Submarines stop at 1,000 meters, not because of engineering limitations, but because matter itself begins to fail. The ocean isn't deep. Your understanding of structural integrity is shallow. Consider the equation. Pressure equals density times gravity times depth. At 10,994 meters, the Challenger Deep this yields 1,086 bars, 15,750 pounds per square inch. A hydraulic press operating on every molecule of your hull simultaneously. Steel doesn't bend here. It collapses instantaneously, folding inward like aluminum foil around a fist. The time between structural compromise and total implosion, 0.003 seconds, faster than your nervous system can register pain. The USS Thresher disappeared in 1963 at 300 meters. Investigators recovered debris the size of dinner plates. The human remains were described in the official report as organic material, consistent with the... This is the technical term for when pressure differentials turn bone marrow into a homogeneous slurry. At crush depth, bodies don't drown. They liquefy before water enters the lungs. Titanium has a tensile strength of 1,400 megapascals. Sounds impressive. The pressure at 4,000 meters exceeds 40 megapascals. You have a 35 by safety margin. Except titanium also suffers from hydrogen embrittlement in seawater microscopic fractures that propagate through the crystalline structure. Every dive weakens the hull at the molecular level. You don't know which dive will be the last. The metal doesn't warn you. It simply ceases to exist as a solid. OceanGate's Titan submersible imploded at 3,800 meters in June 2023. The carbon fiber, hull marketed as revolutionary, experienced catastrophic delamination. Carbon fiber is an anisotropic material. Its strength exists only along the axis of the fibers. Under uniform external pressure, the resin matrix shears apart. Layers separate. Water intrudes between laminae at 1,500 meters per second. The implosion generates a shockwave equivalent to 40 tons of TNT detonating inside a phone booth. The 5 occupants were converted to particulate matter before their neurons could fire. This is not tragedy. This is materials science. The Mariana Trench exerts pressure equivalent to balancing 50 jumbo jets on your thumbnail. No human-made alloy can maintain structural integrity under these conditions indefinitely. Even titanium spheres, the strongest geometric configuration, develop microfractures after repeated exposure. The DSV limiting factor. Currently the only submersible rated for full ocean depth, uses a 90 millimeters thick titanium sphere. It has completed 37 dives. Ultrasonic testing after each mission reveals progressive crack formation. The sphere is consumable. It has an expiration date, measured in cycles, not years. James Cameron's deep-sea Challenger required 12 tons of syntactic foam hollow glass, microspheres suspended in epoxy just to achieve neutral buoyancy. The foam compresses 2% at depth. This sounds trivial. It represents 240 kilograms of volume reduction. That displaced volume must be compensated, or the submersible becomes negatively buoyant. You begin sinking. There is no bottom to rest on. The sediment layer at the Challenger Deep is 1,200 meters thick. It's not solid. You descend into geological ooze until pressure equalizes your density with the substrate. You are entombed in liquid mud under 11 kilometers of seawater. Recovery is thermodynamically impossible. Let's discuss viewport failure. The Titan's forward viewport was acrylic. 21 inches in diameter, 9 inches thick. Acrylic has a compressive strength of 120 megapascal, is exceptional among polymers. But viewing ports are stress concentrators. Every circular penetration in a pressure hull creates a discontinuity where force lines converge. The viewport must withstand not just uniform pressure, but shear forces at the interface with the titanium ring. Acoustic monitoring detected cracking sounds during Titan's previous dives. These were pressure-induced fractures propagating through the acrylic matrix. The crew was warned. They dove anyway. The acrylic didn't fail. It performed exactly as material science predicted. The failure was epistemological refusal to accept that some depths are ontologically hostile to human presence. The Trieste I, submersible to reach Challenger Deep in 1960, was essentially a gasoline balloon attached to a steel sphere. Gasoline is less dense than seawater and incompressible. Elegant, the sphere's walls were 12.7 centimeters thick. It could carry 2 people in a space the size of a washing machine for 20 minutes at depth. The project cost $250 million in 2024 dollars. It has never been repeated at scale because the engineering provides no margin for error. A single weld defect, one impurity in the steel, a microscopic inclusion of slag any of these precipitates instant death. You cannot inspect every cubic centimeter of a pressure hull with current, non-destructive testing methods. You accept risk, or you don't go. Modern submarines operate at 400 to 600 meters. Nuclear attack subs are rated for 800 meters, absolute maximum that never exceed depth. Beyond this, steel undergoes plastic deformation. It doesn't snap back, the hull warps permanently. Bulkheads buckle, seals fail. Water ingress at 800 meters enters at 200 kilometers per hour. It doesn't spray, it jets. A pinhole leak becomes a cutting torch that slices through bone. The pressure differential is so extreme that air inside the submarine becomes pressurized. Crew members experience barotrauma, ruptured eardrum, sinus hemorrhage, pulmonary edema. This occurs before the hull breaches completely. The Kursk sank to 108 meters in 2023. Sailors survived the initial torpedo explosion and retreated to the aft compartments. They had air. They had emergency rations. They wrote notes to their families. They died over 48 hours as CO2 accumulated and internal pressure equalized, with external seawater through microleaks at 108 meters, less than 1% of the ocean's maximum depth. Rescue submarines couldn't reach them because the Kursk was blistering at 17 degrees and the docking collar couldn't achieve a seal. Proximity is not rescue. Depth is finality. There exists a theoretical limit called the crush depth. Horizon, the point where no material configuration can resist ambient pressure. For steel, this is approximately 6,000 meters. For titanium alloys, perhaps 8,000 meters. For carbon composites, 4,500 meters. The Challenger Deep sits at 10,994 meters. There is a 3,000 meter gap between maximum material capability and the ocean floor. This gap cannot be bridged by engineering. It is a fundamental constraint imposed by atomic bonding forces. The electromagnetic repulsion between electron clouds in adjacent atoms determines how much external force a material can resist. Increase pressure beyond this threshold, and you're not deforming the material, you're altering its phase state. Steel becomes amorphous. Atomic structure collapses. You are trying to compress matter to stellar core densities using seawater. Some propose ceramic hulls. Ceramics have compressive strengths exceeding 5,000 megapascals, but ceramics are brittle. They catastrophically fracture rather than deform. A single point loader collision with a hydrothermal vent, an impact with volcanic rock and the hull shatters. Ceramics also exhibit zero ductility. They cannot absorb impact energy. The ocean floor is not smooth. It's a mountain range of tectonic upheaval, scattered with boulders ejected from underwater volcanoes. Navigating this terrain in a brittle ceramic sphere is statistically suicidal. The alternative is unmanned vehicle. The Nereus ROV reached Challenger Deep in 2009. It imploded in 2014 at 9,990 meters due to a syntactic foam failure. Loss $8 million and 4 years of research. But no human died. This is the future. Robots can accept risk, humans cannot. A robot doesn't experience the 0.003 seconds of implosion. It simply stops transmitting data. There is no terror, no biological imperative violated. The ocean doesn't care. It crushes silicon and flesh with equal indifference. You will argue that technology improves, that materials science advances, that we will synthesize alloys or metamaterials capable of withstanding any pressure. This is a category error. You are not fighting engineering challenges. You are fighting entropy. Every system trends toward equilibrium. A submarine is a low-entropy bubble in a high-entropy environment. Maintaining that gradient requires energy. At 10,000 meters, the energy cost of preventing collapse exceeds the energy available from any portable power source. Thermodynamics is not a suggestion. It is a constraint on what universes are permitted to exist. The ocean is 361 million square kilometers, 71% of Earth's surface. Average depth, 3,688 meters. You have explored 5% of this volume. Not because of funding, not because of political will, because matter fails, because pressure is absolute, because some spaces are not for you. The Titan's implosion created a sound wave detected by hydrophones 1,400 kilometers away. That's how much energy is released when equilibrium is restored. The ocean wasn't violent. It was patient. It waited for human arrogance to descend into its jurisdiction. Then it corrected an imbalance. The debris field covers 800 square meters of seafloor. Investigators recovered fragments of the carbon fiber hull. They found no intact human remains. This is not because the bodies were destroyed. It's because the pressure differential rendered them indistinguishable from seawater at the molecular level. You cannot engineer around physics. You can only accept its terms. The submarines will never go deeper because depth is not a frontier. It is a wall. And walls do not negotiate.